Okay, so you have learned in Chapter 5 many integration techniques for computing integrals. And most recently, you learned how to numerically approximate the value of a definite integral using one of our approximation techniques, like the midpoint rule, the trapezoidal rule, and so forth. Well, in section 5.10, we're going to deal with integrals, okay, that are called improper integrals. And finding an improper integral involves computing a limit. And so computing a limit sometimes requires, well, how many remember computing limits back in Calculus 1? Back in Calc 1, you had to compute some limits. Sure, you remember that. But the type limits that often come up and in regards to, well, just limits that can come up, and also in regards to section 5.10 are what are called indeterminate forms. And we have a theorem called L'Hopital's rule that can help us. So, like, for instance, what's an indeterminate form? We'll take a look here at this, this function here. Okay, suppose we want to analyze the behavior of this function near x equals 1. So you have a numerator and denominator. The numerator is the natural log of x, and the denominator is x minus 1. So as x approaches 1, okay, as x approaches 1, and actually I can be a little more specific here. This is what we're trying to find. The limit of the log of x divided by x minus 1 as x approaches 1. Well, as x approaches 1, what does the denominator go to? What's x minus 1 approach in the denominator as x goes to 1? It goes to 0. That's right. That's right, Ange. It goes to 0. Well, what about now the numerator, the log? What about the natural log of x? As x approaches 1, what is the numerator? What does the numerator go to?
0.
That goes to 0 also. So you see, what you have here is you have a situation where you have your numerator and denominator both going to 0 as x approaches 1. But that doesn't mean that 0 divided by 0 isn't equal to 1, or it's not always equal to 1, and we don't even really know what that means, right? What really matters is the rate at which the numerator and denominator approach 0 as x goes to 1. That's going to help you determine the limit. The limit laws that you learned back in like chapter 2 of this textbook don't apply in this situation, because the denominator, the denominator is approaching 0. Okay, so if we move forward a little bit here, okay, if you have a limit of the form where you have the limit as x approaches a of a ratio of two functions, f divided by g, where both functions are going to 0 as x approaches a, the limit may or may not exist, and it's known as an indeterminate form. It's an indeterminate form. Okay. So you saw in chapter 2, well, you saw some simple ones. This is one that probably your instructor would have gone over in Calculus 1. The limit as x approaches 1 of x squared minus x divided by x squared minus 1. So, the numerator factors, right? The denominator factors. And you can simplify out the x minus 1 terms, and you'll get then the limit as x approaches 1 of x over x plus 1, and that equals a half. How many saw problems like that in their Calculus 1? Okay, Javier and Ange remember that? Sure. And that's fine, that's fine. But that works if you have a nice factoring situation. Okay, but if you have a situation where you're trying to find this limit here, you can't do any factoring there. So what we need to do is you have a rule that will help us. So there's a rule called L'Hopital's rule. Now let me bring it up here. Yeah, this is L'Hopital's rule, section 4.5. Take a look at it for a moment. Let me try to get it completely to show. I want it to show completely. So it says L'Hopital's rule. Let me just get this down one. Okay, so it says that if you have two differentiable functions, f and g, differentiable means you can take the derivatives of the functions, and the derivative of the g of x function in the denominator, if that's not equal to 0, except possibly at a, but we're not gonna, well, let's just move forward here. So let's say both these functions, and maybe I'll blow this up a little bit here. Let's say now both these functions approach 0 as x approaches a. Or you could have a situation where both functions approach plus or minus infinity as x approaches a. Then what you have in this situation is, if you're looking at the ratio, if you're looking at the limit of the ratio of f divided by g as x approaches a, you have an indeterminate form. It's either 0 over 0 or infinity over infinity. Well, it turns out that the limit of the ratio of the function of the function f over g is equal to the limit of the ratio of the derivative of the function of f over the derivative of the function of g. Okay, so the limit as x approaches a of f divided by g equals the limit as x approaches a of f prime divided by g prime. It's actually an amazing result. It's an amazing result. And the reason it's true, they can justify it here based on figure 1. So let me talk about that real quick. So figure 1, you have two functions f and g, the pink and the purple and the blue function. And what do f and g, at the top picture in figure 1, what do functions f and g do as x approaches a?
Y equals 0.
What do they approach, f and g, as x approaches a? They approach, that's right, Nathaniel, they both approach 0. They both approach 0, right? So if you look at like a, the value a there, f of a is 0 and g of a is 0. So this is so if we're interested in how the limit of the f over function f over f of g, sorry, if we want the limit as x approaches a of f over g, then this is an example of where, well, f and g are both equal to 0 at x equals a. So, but now look at the second picture. Look at what they're doing. The functions f and g, if you zoom in very close to a, and think about tangent lines to f and tangent lines to functions f and g at x equals a. Okay, those tangent lines are going to have those equations that you see there in the second picture. Okay, so the derivative of your function f at x equals a derivative is a slope, so that's slope m1, And then there's a slope for the tangent line to the function g at x equals a. That slope, that would be the derivative of g at x equals a, and that's m2, m sub 2. So you see in the second picture there, they've drawn the equations, they've drawn the two tangent lines, and for f and g at the point x equals a, and they're the equations too. And so if you take those linear equations, you see any function, I mean, functions, right, are most all of them are curved. But if you focus on a very small neighborhood on the function starts looking linear. Okay, and so the tangent lines in the second picture there in figure 2 will very closely approximate the value, the functions at x equals a. So if I want the ratio, if I want to study the ratio of function f over function g at x equals a, why not just study the ratio of their tangent lines at x equals a? That's what they're trying to that's what they're trying to convey there. And you see, if you look at the let me see here. Let me just hold on. I got a little bit too much highlighted here. Okay, so here are the ratios of the tangent lines, the equations of the tangent lines. The tangent line for function f was m1 times x minus a. The tangent line for the tangent line for function g was m2 times x minus a. And if you look at the ratio of the tangent lines, those equations, the x minus a simplify out to be giving you m1 over m2. And therefore, we're able to say then, I mean, this is an intuitive way to understand L'Hopital's rule. The limit as x approaches a of f divided by g would just be the limit as x approaches a of the ratio of their derivatives. Okay, so are there any questions on that? Okay, good to see you, Sandia. Good, excellent. All right, so are there any questions from this L'Hopital's rule? Okay, from section 4.5. Okay, so naturally, this is being recorded. So those of you that arrived late today, I'll ask you to refer back to the recording. But we've not done any actual problems yet. We've just been talking about L'Hopital's rule here, and the L'Hopital's rule. And by the way, in figure 1, I just want to mention, so those equations of those tangent lines, you know, m1 times x minus a, m2 times x minus a, very good. So, you know, that just comes from the point slope formula. So let me see if I can maybe at least, you know, they give those equations, and I'd like you to just feel comfortable why those tangent lines have those equations. So give me one moment here. Right. Okay. Okay, so there's a line. Okay, there's a line. And on the line, you have a point, okay, which has coordinates A and 0. Okay, and so y minus y1 equals m1 times x minus x1. So that means then that y minus 0 equals m1 times x minus a, and therefore y is equal to m1 times x minus a. Okay, and so in the figure there, figure 1, from a textbook, you know, they just, hey, here's the equation of that tangent line. Well, now you know. Indeed, the point slope form of a line is y minus y1 equals m1, that's slope, times x minus x1, or m. You could just say m, but the point is a and 0, so I'm putting a for x1 and 0 for y1, and then this is going to give me that equation of that tangent line. And so the reason I'm mentioning this is because I think students, when they look at this picture from the book, I think they do a beautiful job of justifying L'Hopital's rule. The two tangent lines for functions f and g have those linear equations, and if you look at the ratio of those linear equations, okay, right there, the x minus a simplify out, and you're left with the ratio of the slopes. And therefore, this suggests then that the limit as x approaches a of f over g is simply the limit as x approaches a of f prime over g prime. And that's the L'Hopital's rule. So what I'd like to do now is I'd like to do a few problems with you. Okay, so let's go ahead now. Now it's time for notes. Okay, let me give you a moment to copy this down. Okay, hold on, we have a few chat messages here. So Calc 1, normally, most Calc 1s do not, Calculus 1, Math 181, at least at Montgomery College, we don't normally cover section 4.5. We wait to cover that in Calculus 2, but some professors still do cover it in Calculus 1. Now, let's see here. Also, there was a question. Right, okay, good. Okay, so how many recall in Calculus 1, how many recall finding this limit here as x approaches a of sine of x over x? How many recall doing that using a geometric proof? That was sort of, it's less common to see that in Calculus 1, but some professors still do it. I don't know, how many recall looking at that limit, maybe in Calculus 1? Okay, Ange remembers it, Sandia remembers it. Okay, and if you recall, using the geometric proof, it was somewhat involved. Okay, well, this is going to be much easier if we use the L'Hopital's rule. So what kind of indeterminate form is this? Okay, this is an what is the indeterminate form? Is it 0 over 0? Is it infinity over infinity? That's right, Taj. It's 0 over 0. That's right, Sandhya. Because the sine of x, as x goes to 0, that function approaches 0. And x itself approaches 0 as x approaches 0. So this is a problem where we can apply L'Hopital's rule to find the limit. Okay, so let's go to the solution. Okay, let me give you a moment to copy the solution down, and then I'll talk about it. Okay, so let's take a look here and see what's going on. One moment, one moment. Okay, excellent. So, all right. So we have this indeterminate form. Okay, I mean, the sine of x is our function f, and the x is our function g. Okay, and both functions f and g approach 0. So our indeterminate form is 0 over 0. This means we can apply L'Hopital's rule. So above this equal sign, I put an H with a circle on it. That means I'm applying L'Hopital's rule. Well, L'Hopital's rule says the limit of the ratio of f over g is equal to the limit of the ratio of their derivatives. So the limit of f over g is equal to the limit of it equals the limit of f prime over g prime. Well, the derivative of sine is cosine, the derivative of x is 1. And so now you have the limit as x approaches 0 of the cosine of x. Well, that's just, there's nothing strange about that. That's a continuous function. All we need to do is put in 0 for x, and we get 1. That's exactly right. That's right, Sandia. So, are there any questions on that one? On that particular problem?
Yes, Professor, I have a question.
Yes, Taj.
I understand how L'Hopital's rule is supposed to work and how we're supposed to use it generally. I thought this specific limit was we weren't allowed to use L'Hopital's rule here because in order to find the derivative of sine x, like to begin with, you end up needing to compute this limit.
Um,
Like if you use the definition of the derivative on sine x, I think this limit ends up coming in there somewhere.
no, it's this is all you need to do. This is I mean, L'Hopital's rule says that that this is okay. I mean, it's for indeterminate forms like 0 over 0 or infinity over infinity. I mean, it is like that. It's not gonna. Let me just see here. Hold on. Let me just try some here. One moment. One moment. I'm just seeing if yeah, it's not going to work. Like you have to have you can apply L'Hopital's rule when you have these indeterminate forms. So it isn't like something that can be used for any function f and any function g. F and g have to both be approaching either 0 or they're both approaching plus or minus infinity as x approaches a. All right, Taj, is that
Yeah, that
is that
answers my
okay?
question. Thank you.
Okay, all right, you're welcome. You're welcome. Let's look at another example. Let me give you a moment to copy this example down. Okay, so this is an interesting problem here. Here we don't have we don't have the ratio of two functions. We have the product of two functions. Okay, here we have a function x times another function, the sine of pi over x. Okay, and let's see. So if I write, if I think about this, what's the limit as x goes to infinity of x? What's that equal to?
Infinity.
Infinity, clearly. All right. Also, what's the limit as x goes to infinity of the sine of pi over x? What's that equal to?
0.
That equals 0. Because pi over x, that's right, Ange, pi over x goes to 0 as x gets large, and the sine of that, the sine of an angle approaching 0 would be 0, so because the sine of 0 is 0. So in this situation, you have something a little different. You have a different indeterminate form. You have a function approaching infinity as x goes to infinity times another function that's approaching 0 as x goes to infinity. Okay, so this is your indeterminate form for this situation. Now for this one, we can't use L'Hopital's rule for that directly, because L'Hopital's rule is only for situations where you have 0 over 0 or plus or minus infinity divided by plus or minus infinity. So what we have to do is we have to manipulate this equation a little bit, or this limit. And let me show you how we do that. I'll go to the next page. Are there any questions so far? Okay, to the next page then. So, all right. So what I do is I'm going to get a ratio of two functions. So, and you notice I keep, I have the limit of x times the sine of pi divided by x equals the limit of x times the sine of pi divided by x over 1. I don't I keep the limit there because I haven't taken the limit yet. Well, what I'm going to do is I'm going to multiply by 1 over x in the numerator and 1 over x in the denominator. Okay, and if I do that, now watch what happens. This x here will simplify with this x, and I'm left with the sine of pi over x in my numerator and 1 divided by x in my denominator. Okay, are there any questions up to this point? All right. Well, so do we have an indeterminate form here? Do we have an indeterminate form of, say, 0 over 0? If this is I'll call this my function f, sine of pi over x, and 1 over x is my function g. Do I have an indeterminate form here? Does the numerator approach 0 as
Yes.
x goes to infinity? It does.
Yeah.
What about the denominator? Does it approach 0 as x goes to infinity?
Yes.
It does. So I have an indeterminate form that I can use L'Hopital's rule on. Okay, I have an indeterminate form. So what I'm going to do is I know I'm going to have to take the derivative of f and the derivative of g. Before I take the derivative of f, I'll rewrite f. I'll rewrite it a little more simply. I'll just write it as the sine of pi times x to the negative first. I'll just, and then in the denominator, 1 over x, I'll write as g. I'll write it as x to the negative first. And now I will take the derivatives. Okay, so in the numerator, the derivative of the sine of pi, the sine of the angle pi times x to the negative 1, that's f prime, right? That's f prime there. And then the derivative of x to the negative first, that's negative x to the negative second, that's g prime. Please let me know if you have any questions so far. So these are my derivatives. All right, those are my derivatives. And, well, some nice things happen here, right? The x to the negative seconds here simplify out. Okay, the negatives simplify out too. And I'm left with then pi times the cosine of pi over x. And that will just equal then pi times 1, which is pi. And we found the limit. Okay, are there any questions at all on this here? Are there any questions?
Professor, I can we use can we use substitution so that you don't get x going towards infinity, instead you get u going toward 0 with u equal 1 over.
Well, there are ways you can use a substitution for the limit. You can make a substitution, but that generally is not what we do. It
Okay.
usually doesn't gain you anything. Usually, sometimes it might, but usually it doesn't. It's best just to use L'Hopital's rule directly. But that's a good question, Ange. Good question.
Mm-hmm.
All right, well, if we're good here, let's go to the next problem. We're doing some examples here from section 4.5. Let's take a look at this example. Okay, so let's see here. Let's see. So, how is the how is the sine this or the secant of x defined? Secant of x is, that's good, 1 over the cosine of x. Very good, Nathaniel. Very good, Taj. And what about the tangent of x? How's the tangent of x defined? Good. That's the sine of x divided by the cosine of x. Okay, so usually these problems, it's going to help to write secants and tangents in terms of the, fundamental trig functions, sine and cosine. So here we're looking at the limit as, that's right, Sandhya, that tangent could also be 1 over cotangent of x. In this case, I'm going to write tangent as sine of x over cosine of x, because what do you think I haven't taken the limit yet, but what do you think I want to do with these two fractions here that have common denominators? What do you think I want to do with them?
You're gonna write 1 minus sinus over cosine of x.
That's right, Andrew. That's right. We're going to combine those fractions. We're going to combine them. So let's go to the next page here. Let's go to the solution here. And hopefully the first 2 steps are clear. This step and this step. Okay, let me give you a moment to copy that. That's correct, Sandhya, in regards to the limit. Well, now hold on. Wait. This, let me just check. Let me just check one thing. One moment. So the sine, this here means we're approaching pi over 2 from the left side. Okay, we're approaching pi over 2 from the left. Okay, that's what that means. If it were a plus up there, we'd say we're approaching pi over 2 from the right. Now, let me ask you, as we're here, as x approaches pi over 2, what does 1 minus the sine over x approach? What's that approach as x goes to pi over 2? Well, what's the sine of 90 degrees? 1. So 1 minus 1 is 0. So this is approaching 1 minus 1, which is 0, right? The numerator is approaching 0. What's the cosine approach as x approaches 90 degrees? What's the cosine of 90 degrees? That's 0 also. So, okay, we can use L'Hopital's rule. We have indeterminate form 0 over 0. Very good, everyone. So I'm going to apply L'Hopital's rule. So I put the h over here, and the derivative of, again, 1 minus sine is my f, cosine of x is my g, negative cosine of x is f prime, and negative sine of x is g prime. So what you get here, well, now we can take the limit, because you see, if I were to put in a little more detail here, I can write this limit. I can write this limit as a ratio of two limits. Okay. Because the denominator is not approaching 0 as x goes to pi over 2. And so you get 0 over 1. The answer is 0. Another way to think about it is if you were to, if you this negative cosine over negative sine, as one of you pointed out, that whole ratio is the cotangent of x. And if you look at the graph for the cotangent of x, if you type in your calculator, y equals, that's right, Sunday, if you type in y equals 1 over the tangent of x and graph that on your calculator, make sure it's in radian mode, you'll see that as x approaches pi over 2, the cotangent of x equals 0. It's another way to look at it. At any rate, we found this limit. So you see, L'Hopital's rule is helping us tremendously. It's helping us tremendously in finding limits. Are there any questions? I'd like to do one more, and then we can take a little break here, but let's try to get one more in. I got two examples. Let me try to get one of them done here. All right, let's look at this one. Take a moment and copy that example down. Okay, while you're copying, Sandia had a question. Yeah, the remedial problems are due officially this Friday at 2:55 p.m. Yes. I will be making when we go on our break, I'll make one comment before you go to break about a comment I think I'll make it. But let me copy this. Okay, and Sunday, I'll address that during the break. Good question. Okay, so we have now the limit of x times e to the 4 over x power minus e to the x power. And what we're going to do here, sometimes I look at these L'Hopital rule problems as like little puzzles. We want ultimately 0 over 0. We want our expression to be an indeterminate form of 0 over 0 or plus or minus infinity over plus or minus infinity. And I certainly don't have that here. But I can factor out an x. I can factor out an x, certainly. And this may help us. So sometimes, you have to just try something with these L'Hopital rule type problems. You have to try something. And, but the goal always is to get the function or the expression in one of these two or well, one of those indeterminate forms. So let's see how this one works. I'll go to the next page. Okay, so we're factoring the x. And what I'm going to do again is I'm going to multiply. Well, I need to have a fraction. I need to have a function on the top in the numerator and a function in the denominator. So I don't, this x here is kind of a nuisance, could be a nuisance. So let me multiply by 1 over x on the numerator and denominator. And if I do that, we get some simplification here. The x's simplify out, and I'm left with, on the numerator, e to the 4 over x power, or e to the power 4 over x minus 1. And then in the denominator, I have 1 over x. And if you don't mind, I'll write that. Well, let me ask you, as x goes to infinity, what does 1 over x go to as x goes to infinity? Good, good, very good. It goes to 0. Okay. What does e to the 4 over x power, what does it go to? So now I'm studying the numerator. E to the 4 over x power, okay, it's going to go to 1. It's going to go to 1 as x goes to infinity. Because the 4 over x, basically as x goes to infinity, 4 over x goes to 0. And e to the 0 power is equal to 1. So now 1, and then 1 minus 1, you know that, well, you know what I mean. Something approaching 1 minus 1 goes to 0. So this is in good form to use L'Hopital's rule. But before I use L'Hopital's rule, since I have to take derivatives, let me write those fractions as exponents. 4 divided by x can be written as 4 times x to the negative first. And 1 over x can be written as x to the negative first. And then it's so much easier to take the derivatives of the numerator and denominator. Please let me know if you have any questions. All right, well, so we differentiate the numerator and denominator. Let me just see here. So this is all being multiplied up here, right? So I had to use the chain rule to find the derivative of the numerator. And then, you know, nice things happen here. We get some simplification. So that's going to get me 4 times the power e, 4 times e to the power of 4 over x. And as you let x goes to infinity, that approaches 4 over x approaches 0. So you get 4 times e to the 0th power when you take the limit. Notice when I actually take the limit now, I then drop the limit sign, right? I carry it all along in the problem until then when I take the limit, then I can drop the limit sign. So I'm going to get an answer of 4 for my limit. Okay, are there any questions on that? Okay, who's feeling comfortable so far with L'Hopital's rule? Who's reasonably comfortable? Okay, Sandia is, and Ange is, good. And Taj, wonderful. Okay, well, let me stop the recording then.